When testing automated driving systems, real-world testing is the de facto standard, as it enables us to evaluate the systems realistically. At the same time, it comes with some drawbacks, such as high risk, high cost, and non-repeatable experiments. To solve these issues, dataset testing is the most common solution, in which an experiment is recorded in the real world and then transformed into a dataset which then can be replayed multiple times safely. The issue is that this methodology is open loop. An alternative is simulation-based testing, which solves the dataset testing problem, being a closed-loop methodology, while being safer and cheaper than real-world testing. At the same time, this is an approximation of reality. As such, it comes with some drawbacks. They are identified in the reality gap problem, the difference between simulation and reality, and the resulting difference of behavior of the system under test. In this work, we will concentrate on differences of sensor data and scenarios. It is in this context that we propose Cam2sim, a tool that combines the realism of sensor data and scenarios of dataset testing while being closed-loop and repeatable like simulation-based testing. At the high level, Cam2sim consists of three main steps. First of all, dataset processing from real-world data. Then we have scenario reconstruction in simulation. Finally, we have our full pipeline in execution, in which we use generative AI to transform simulated data to look like real-world one. Let's dive a little bit deeper. First of all, in this work, we need real-world data, both as a reference and to be reconstructed in our tool. To do that, we have deployed Dave2, an end-to-end driving model developed by NVIDIA. We deploy it on a real self-driving vehicle on a public street. The first step of our pipeline is an optional ROS-bag extraction tool, which extracts localization, camera data, but also optionally LiDAR data to then perform our pipeline steps. The second step of our pipeline is dataset processing, which we use to extract non-labeled data from our dataset. These include the localized images, which are a combination of camera frame and where it was taken. Then we extract an OpenStreetMap OSM file using the localization data. This will be used to extract the ego trajectory and map data, then used for scenario reconstructions. Finally, we perform parked vehicles detection, either using camera or LiDAR. Using the map data and the parked vehicle data, we can then generate a CARLA simulation. Instead, in step 4, we will use localized images to train a Gaussian Splatting model. We will use CALMAP in combination with NeurStudio. With CALMAP, using each of the frames recorded from our vehicle camera, we will infer relative localization and then use it to train our Gaussian Splatting model in NeurStudio. Once all preparation steps are done, we can then go into scenario execution. We have two main possibilities, either using CARLA simulation on its own or in combination with Gaussian Splatting to improve realism of image frames. Each of the two options allows us to use either trajectory replay, in which we will reposition the ego vehicle in each of the localizations that were found in real-world data, while the second option is running the system under test in the loop. Here you can observe script 5A. This is trajectory replay of the real vehicle positions in CARLA only. Here instead you can observe the complete pipeline in the works. This is script 5D, in which we perform closed-loop ADS testing using Gaussian Splatting for image improvement. Here the system under test is providing outputs directly to simulation, which is enacting them, producing a simulated image, which then is translated with Gaussian Splatting and fed back to the system under test.